Good evening, everyone. Thanks for coming out on this kind of crummy night. My name is Roger Moore, and tonight is the real North Star. The title is, there's a little satire in that title. I mean, we're all somewhat familiar with the North Star, although when we ask people to locate it, they often have trouble finding it, or think that it's a brighter star than it actually is. So we'll talk about that. Our North Star is actually not a single star, it's a system of stars, and there's some unusual properties to it, so we'll go into that. And it's also the North Star that we have now has not always been the North Star and won't always be the North Star. So we'll talk about why that happens and implications that has for astronomy. So of course I'm talking about Polaris, which is in the constellation of Ursa Minor. This is a view, if we had a clear night and you went outside and looked north, this is what you'd see, minus the labels and lines. But the North Star is located at the end of the handle of the Little Dipper. Now, unfortunately, we can't see most of the stars of the Little Dipper, so we need a different way to find the North Star. But it's visible all night, on any clear night, from northern latitudes. So once again, this is what it would look like if you could go outside and look north right now. So the Big Dipper is handle down, probably be right over the school. And why is it called the North Star? Well, because Earth's north axis of rotation points almost right at Polaris. Not quite, but almost. The name is derived from Stella Polaris, the Latin, or pole star. And it's not one of the brightest stars. It's only about the 48th or the 50th, depending on who you ask. So this is a list of the 50 brightest stars, and there's several of these that are up tonight. Unfortunately, we won't be able to see them. Sirius, which is the brightest star in our night sky, is up right now. Pollux and Castor, which are both in Gemini, they're both up in the sky right now. And let's see, Rigel and Betelgeuse, both in Orion. They are both up in the sky right now too. Betelgeuse is a very interesting star. It's a red supergiant that they know will eventually end its life as a supernova. And it's a variable star. That is, it brightens and dims over regular periods of time. Not enough that the casual observer would notice. But in the last 2 or 3 months, Betelgeuse has dimmed significantly. It's dimmed much more than anybody has seen before, and they're still trying to figure out what that means, why that's happening. But you have to go all the way down here to the bottom right of this list to find Polaris. So it's not a particularly bright star. It's been used by sailors and explorers for centuries for navigation. And because it is at the north rotation axis, if you measure the angle to Polaris from the horizon, that also equals your latitude above the equator. So the further north you go, the higher Polaris gets in the sky, till you get to the North Pole and it's directly overhead. The further south you go, the lower it is until you get to the equator where it disappears. Unfortunately for the southern hemisphere, they don't have an equivalent star, a corresponding South Pole star. The closest they have is a much dimmer star that's farther away from the pole. So how do you find it? Well, everybody can recognize the Big Dipper, and all you need to do is find the end of the bowl. Starting inside the bowl and working your way out, you follow those 2 stars, and it'll point you right to the next brightest star, which is Polaris. The beauty of that system is that it doesn't matter which way the Big Dipper is facing. The same thing still works. Start at the bottom of the bowl, work your way out, and it'll point you right to Polaris. So once you know Polaris, then you know all 4 different directions. So it's easy to find it. And you can get a rough idea of your latitude, that is how far above the equator you are, simply by using your fist. An adult's fist held out at arm's length covers about 10 degrees of the sky. So you put the bottom of one fist on the horizon and you just stack them like this until you get to Polaris, which works out to be about 4 and change from our latitude. And that's about our latitude. It's about 41.5 degrees north. So we'll show you a little video. This is what you would see if you could stand and face north and watch the sky for 24 hours and ignoring sunrise and sunset, you'd see what happens. And while we do this little video, watch what happens to Polaris, which is right there, and watch what happens to the Big Dipper. So notice Polaris does not appear to move at all. And the Big Dipper never goes below the horizon, again from our latitude. And also because of this, anyone with a digital camera and a tripod can do cool things like this, where you just point your camera at Polaris, take a series of long exposures, this was 90-second exposures, and then stack them together in software, and you can see for yourself Earth rotation. So Polaris is about a 70 million year old triple star system. Polaris A is the main star, that's the one we see. Polaris B, which you can see in most small telescopes, was discovered by William Herschel in 1780. Going back to about 1930, they knew that Polaris A had a close companion because of the way it wobbled in the sky, but it wasn't until 2006 that the Hubble telescope actually imaged this closer companion, Polaris AB. So Polaris AB is only about 3 billion kilometers from Polaris A. Big numbers, but when the Earth and Pluto are on the same side of the Sun, they're about 3 billion kilometers apart. So the distance between those two stars is only the distance between us and Pluto. So it's not a remarkable star in our skies, but it is an enormous and very bright star. It's what's called a yellow supergiant star. It would be about 2,500 times brighter than our Sun and about 40 times wider. But it's far away. It's almost 480 light years away. It is also the closest Cepheid variable. Cepheid variables are stars that brighten and dim on a regular basis. And they are one type of star because of this relationship that was discovered by Henrietta Leavitt. The rate of their variability is related to how bright they actually get. And because of that, astronomers can use Cepheid variables to estimate distances, stellar distances. So it's one of the rungs of the distance ladder that they have. With Polaris, though, Polaris is not one that they use to measure distances because Polaris has a variable rate, and they're not quite sure what's going on there either. So just a little diagram. There's our Sun, and there's what Polaris would be sitting next to it. Again, it's an enormous star. That's Polaris A. So why has it not always been the North Star? Well, if you take a spinning top and you give it a little nudge, it'll do this wobble they call precession. If you give the spinning Earth a little nudge by gravity from the Sun or the Moon, it will also wobble and go through precession. So the Earth has the same kind of a wobble, so the north polar axis traces out a circle in space, which means it constantly points at different stars. It's about a 26,000 year cycle. So this would be looking northwest about this time of year. I chose this time because all the stars I was interested in were still above the horizon. So there's Polaris right there. Subin, which was the North Star around 3000 BC, is right there. Alderaan, which will be the North Star 7500 AD. Vega, it'll be the North Star 14,000 AD. And this last one right above the horizon is Tao Hercules. So if you connect them with a circle, that shows you the amount of wobble that the Earth has across the sky. Notice that some of these, I tried to do this as accurately as possible. Some of these, the star is real close to the axis of rotation. Some they're pretty far away, like Vega won't get as close to the actual North Pole as Polaris is, and Polaris won't get as close as Subin was. So we'll talk about those stars briefly. Subin is an eclipsing binary. That is, it's two stars that are orbiting around a common center, and they're oriented in such a way that from our point of view, they cross in front of each other. It was the pole star when the Egyptians built the pyramids, and one of the theories they have is that the Egyptians waited to a certain time of night, and there's two stars that orbit that circle around Subin that they call the indestructible stars because they never set. And they waited until these stars were lined up just right, and then used that to orient the north side of the pyramids. This one's about 300 light years away, and Subin was more closely aligned with the North Pole than Polaris will ever be. So this is what the Egyptians would have seen looking north in the evening. Subin is that dim little star right there. So that was the center rotation at the time. The two indestructible stars are Kokab and Mizar. They would circle around Subin, so they wait till a certain time of night where they get this alignment and use that to orient the north side. Alderamin, it's the brightest star in Cepheus. It will be the pole star in 7500 AD. It's a white giant, 49 light years away. Rapidly spinning star though, it spins once every 12 hours, as opposed to our sun, which takes about a month to do a complete rotation. Vega, that's in Lyra. It will be the pole star in 14,000 AD. It's one of the three, if you come in the summertime, we always point out the summer triangle, and Vega is one of the three stars in the summer triangle. It's relatively close, 25 light years away, so it's the fifth brightest star in the sky. And if you ever saw it was an old science fiction movie called Contact. It was based on a Carl Sagan novel, starred Jodie Foster. Well, she supposedly received a radio signal that came from the direction of Vega. And the last one, Tao Hercules, is in the constellation Hercules. It's either a double or a multiple star, they're not real sure, about 300 light years away. And it will be the pole star, or was the pole star in 7400 BC. I'm always amazed at what some of these ancient scientists could accomplish. This idea of precession, the Earth's wobble, was first discovered by Hipparchus, who you see when he lived. He was a Greek mathematician and astronomer, and he took careful measurements of the positions of the stars and the position of the sun during the equinoxes, and compared that to much earlier records that he had access to, and realized that everything had shifted. But not only could he measure this, but he also was able to figure out why it happened. And it's just pretty amazing. So what does that mean for astronomy? Well, the problem with this wobble is that it makes celestial objects appear to shift position in space. So we have, if you want to locate objects on the Earth, you have our terrestrial coordinate system, latitude and longitude. Latitude's based on the equator as 0. Anything above it is positive. Anything below it is, or anything above it is north. Below it is south. And longitude is based on a line that runs through Greenwich, England. So you have east and west longitude. Well, we have a similar coordinate system for celestial objects called celestial coordinate system. And the easiest way to appreciate this is to imagine Earth as being inside a gigantic sphere. And all the celestial objects that we look at are on that outer sphere. So we can also put a coordinate system on that outer sphere. But what we use is, for baseline, we use a projection of Earth's equator out into space, and that becomes the basis for anything above and below. And rather than latitude, we call it declination. And we also, and for longitude, which is called right ascension, we use a point where the sun crosses the equator at a certain time of year. And that becomes the longitude 0, or the right ascension 0. But the problem is, as Earth precesses, it wobbles, or the projection of Earth's equator in space changes. And I'll show you that to you here. So say you want to look at an object now, and you look up the coordinates, and it tells you that it's right there. It's on the celestial equator. So it would have 0 degrees declination. 20 or 30 years later, you want to go back and look at that same object. And I'm going to exaggerate things here, but Earth is now wobbled some. Rotation axis has changed. The projection of Earth's equator in space has changed. So now if you go and look for something that's 0 degrees declination, your telescope would go here, but that object you were interested in is still up here. It hasn't moved. So the objects in space don't move, it's just the reference system that we use has moved. So what do? Well, they update the coordinates to all these objects about every 50 years. The current one we're using is called J2000. The previous one was 1950. But even 20 years later, if you put those coordinates into your computerized telescope, the 2000 coordinates into a computerized telescope and tell it to find that object, you'll probably still find it. It'll probably still be in your field of view. It won't be in the center, but it should be somewhere visible. So that's good enough for just casual observing. But if you need to do real science, then you need software which can update these coordinates in real time, and that's something that we can do here. So 2050, well, there may not be a 2050 set. The International Astronomical Union has agreed to change the coordinate system. Rather than using this variable reference system of Earth's equator, they're going to base the measurements on fixed objects in space, certain radio sources and certain stars. So that way the whole coordinate system won't change over human lifetimes. But we'll see. It's a controversial subject, and maybe they'll do it, and maybe they won't. So what about the rest of the planets? Do they have the same wobble to them? Well, there's scant information out there about the rest of the planets, but I was able to establish that everything except Mercury and Venus have the same kind of a wobble. In fact, Mars wobbles some 10 degrees, and that has caused some dramatic climate changes in Mars. Mercury and Venus, probably not. One of the prerequisites is that the planet has to be spinning fast enough that it becomes oblate. That is, it's wider at the equator than it is at the poles. And Mercury and Venus both rotate very slowly, and they're both almost spherical. So they probably do not precess. But all of the planets have an orbital precession. So you know they orbit around the sun in an elliptical orbit. Well, the long axis of that ellipse also rotates around the sun. And then just last thing here, this is not totally relevant, but I thought it was interesting. We already talked about this precession, Earth wobble. Earth also changes its obliquity, that is, its tilt to the orbit of the plane, to the orbit of the plane around the sun. So it tilts over a 40,000 year cycle, the tilt changes. And also the eccentricity of its orbit around the sun changes. It goes from being elliptical to almost circular and back again over a 100,000 year cycle. Each one of these cycles influences how much sunlight reaches the northern hemisphere, and which has most of the landmass. So some of these cycles increase the amount of sun that the Earth receives, and some decrease it. But every once in a while, over thousands of years, these cycles can line up just right and lead to prolonged periods of extremely warm temperatures, or they can line up just the other way and lead to long periods of extremely cold temperatures. So just to summarize, Polaris, our current pole star, easy to locate, not a particularly bright star, but it's easy to locate once you find the Big Dipper. And our precession wobble has led to different pole stars over the years. All of the planets have an orbital precession around the sun, and some of these various cycles can line up, leading to significant climate changes on our planet. They're known as Milankovitch cycles, after the geophysicists who first realized their relationship. Any questions? Joe, can you get the lights, please? Thank you.